University of Pune in 2002. Work as a CSR RA 2002 to 2003, was awarded Fast Track Project for Young Scientists by DSP during 2004 to 2007. After that, she served as a lecturer in Department of Chemistry, University of Pune, 2007 to 2008, for a year before joining as a regular faculty in 2008. She carried out her postdoctoral research at Duke University, USA, during 2010 to 11, under Boyce Fellowship conferred by DST, Government of India. She is the exam board member for Indian Chemistry Olympiads conducted by Hobi Bhabha Center for Science Education, Mumbai, since 2016. She was a member of Indian delegation to International Chemistry Olympiad held in Thailand, 2017, as a scientific observer, member of study group Bal Bharati Chemistry Textbook for Standard 12, 2019-20, member board of studies chemistry, SP College Pune and Pratap College Amalner. She has over 40 publications in peer-reviewed national and international journals. 4 students have been awarded PhD degree and 3 are currently working. Her research area are synthesis of fluorophore-labeled metal complexes for bioimaging as a probe for cellular organelle cells, investigating their photochemistry, metal-based antibacterial agents, and development of sensors for environmental and biosensing applications. Using absorption, emission, lifetime measurements, time-correlated single photon counting, electrochemical, EPR, confocal microscopy, and single crystal X-ray diffraction techniques. With this introduction, I request Professor Kumbhar to start the lecture.
Thank you, Dr. Arbuz, for the kind information. And at the outset, I would like to thank CMATE for giving me this opportunity to interact with the students, because being a teacher, it is always a pleasure to interact and reach to a wider student population. And this I really like. Okay, so the students are tomorrow's teachers, scientists, the investigators, and everything. So, yes, Arbuz, can I have the access to share the screen? One part.
Madam, access is given to you, madam. Just share your screen.
No problem. Okay.
It's coming now.
Yes.
Yeah, slides are visible, madam. Just do slides.
And dear students, good morning to all of you. And yes, I think the slides are quite clear. Okay. So today, the topic that has given to me is physical and chemical properties of nanomaterials. But I do not know how many lectures you have had it before and how much in depth you know about the nanomaterials. So what I would be doing is, first I will touch upon with the basic properties of nanomaterials, like what materials are called as nanomaterials, and then I would slowly go into the different properties. And again, I have been told that the properties that are shown by nanomaterials would be covered in depth by other members who would be delivering talks in this series. So I would not going much into details of that also, because everything is not possible to be covered in 45 minutes time frame. Okay, so let us start.
Yes, ma'am.
Yes. So the outline of my talk is, I would be first telling you about what do you mean by nanoparticles and why the small is good. And after that, we will be going through various physical properties and some of the properties that I have mentioned, like mechanical, electronic, optical, and magnetic properties. Before going into looking at what are the nanomaterials, let us talk about few things which we need to do or which we need to understand. Because when we are going to work with micro and nanotechnologies, it is important that we should have some understanding about the size and the scale on which these materials are. And this in general will help us in understanding the processes and the applications wherein we can use such kind of materials in the microtechnologies or nanotechnologies. It will also help us in defining what exactly do you mean by microtechnology or nanotechnology. And then we can identify, or it will help us in identifying the objects which fall within that range, and based on that we can look upon for suitable applications in micro and nanoscales. So what is a nanoparticle in the first place? Nanoparticle, they define it as any material that has at least one of its dimension in the range of 1 to 100 nanometers. Okay, so that is the definition. And from where this term came into picture. So nano, that term is derived from a Greek word nanos. That means a dwarf or a small, tiny thing. And a Japanese scientist, Norio Taniguchi, he in 1974 first coined the term nanotechnology, and then onwards we are using this term on a routine basis. So we need to know about the dimensions, right? When we are talking about nanoparticles. So a nanometer is nothing but 1 billionth of a meter. Look at the tiniest size of the nanoparticles. And why do you, or the why we in general would like to know about the properties of these, right? So there has to be some aim, and the aim is looking at the characterization that people carried out in the initial phases after the discovery of these nanoparticles. They were amazed to see how different the properties are of these new materials than the bulk materials we were looking at. And they were looking at different applications, and that is why the studies of such nanomaterials in developing what we call now as nanotechnologies is very essential. And is it new? Is it really new? That is what one has to ask. And if you look at this slide here, we can see that the things that are present naturally and the dimensions. And on the right hand side, I have given a list of nano materials which are made by us, that are man-made materials. And in between there is a scale. Okay, so yes, so if we go from 1 centimeter down to 1 nanometer over here, right? So our nanomaterials fall within the range of this 1 nanometer to 100 nanometers here. It is the small range. And we are dealing with the materials of different sizes from uh, like kilometers to down to now nanometers or few femto. So the ant, the size of an ant is about 5 millimeters. The mites which are present in dust or in the linens or bed linens that we find is about 200 micrometer. If you go down to human hair, it is about 60 to 120 micrometers wide. Whereas the fly ash, which we consider as a tiny particulate matter, has a dimension of about 10 to 20 micrometers in it. Okay. Then we go down to our red blood cells, which has dimension of about 7 to 8 micrometers. And from red blood cells, if we go down to the enzymes and proteins that are present in our body, which acts as efficient catalysts, right? Then the sizes go down to 10 nanometers in diameter. Look at now the efficiency with which these enzymes they work. The rate with which they catalyze the reactions in our body are of the order of 10 to the power 30, 40, 50 per second. So those many molecules are catalyzed and converted into the products. In many cases, the products are not harmful to our body. Okay, so they are taking care of wellness in general of a human body. And why the rates are so high? If you look at the dimensions, that will give us the answer. And if you go down to DNA, that is a genetic material, okay, it is of the order of 2.5 nanometers in diameter, right? So, as nature itself has a varied dimensions which has been put into different applications, now the having access gained towards these biological materials, people have started thinking, oh, is that so? So if we go down from the macro to micro, the properties are changing and the efficiency of these materials is enhancing. Is it possible for us to do it in vitro? And the search for that began. Okay, so here, if you look at the things that we have made, the head of the pin was initially considered as the tiniest one. Okay, but it is about 1 to 2 millimeters. Now, for us, when we are talking about nanotechnologies, this is quite high. And then micro electromechanical devices that came into picture afterwards, they have the dimensions in the range of 100 to 10 to 100 micrometers. After that, as the discoveries continued, we have found the materials which are in nanometer dimensions, and people have shown various applications of these materials. So here I have prepared a table. Now, being a student and having seen this picture, is it possible for you to tell me a name of a compound or a material which would fall in either of these categories, a macro, micro, and nano? I have given 3 4 examples. So looking at those examples, is it possible for you to at least tell me one name for a macro, then micro, and a nano material? Yes, can the participants be unmuted because this could be an interactive session? Not always, but sometimes in between.
Yes, madam, we can unmute the participant, but
Yes.
after
Or
finishing lecture, we will unmute all the speakers,
okay, no problem,
all
no
the
problem,
participants.
no
Okay.
problem. Dear students, you please think about it and tell me the answer. Okay, at the end of the lecture. And then when we are talking about the sizes, what are the differences between the micro and nanotechnology? So here, in addition to the actual size of the objects, the fabrication of the devices is another factor that is of primary importance. Okay, so nanotechnology normally uses what is referred to as the bottom-up approach in the fabrication, that means synthesis of the materials. And microtechnology normally uses the top-down approach. That means it is not like that we cannot use top-down approach for the synthesis of nanomaterials in general. But most of the times people have found that the materials that are produced when we apply top-down approach are of micrometer diameters. But that approach can also be used for the synthesis of nanomaterials. Apart from this top-down and bottom-up approaches, which are very common, there are various or variety of techniques that can be used to synthesize nanomaterials in different forms, like nano sheets, nano spheres, or nanorods, etc., etc. And based on the synthetic procedure that we are using, we can control the size and shape of them, which is reflected further into their properties. So when we are talking about the bottom-up approach, that means a structure, the nanomaterial is made by building atom on atom, okay, or molecule by molecule, from bottom up, so from tiniest to then going in higher dimensions. So each individual atom or molecule in such cases is manipulated or controlled for the correct placement in the devices or the materials that are being made. So when we say that it is a bottom up approach, can we relate this to a natural system or any living object that we come across on day-to-day basis? One example I have given over here, the cells of a seed. Okay, so from a tiny seed, a full grown tree grows up. It takes some time, but yes, from a single cell, you get multiple cells. Okay, so from a tiny molecule, you get a big molecule. That is a bottom-up approach. And this tree continues to grow by taking the individual atoms and molecules and assembling themselves into different parts. Okay, so that is the growth. Now we look at top-down approach. And this approach considers the selectively removing the material from a bulk until a desired structure is achieved. So that means you have a bulk material, you treat it in such a way that it goes from the bulk to the tiniest possible particle size. And one of the applications where this top-down approach is being used is in fabricating the semiconductor devices. Okay, and we can apply that to achieve specific patterning and etching, and we can therefore use such kind of materials in building the electrical circuits. Okay, so they are the tiniest parts in the electrical devices or electronic devices that we use, including our mobile phones. Okay, now you look at the sizes of these devices that has reduced. Okay, it is because of the advancement into the technologies. Now, what does the top-down approach sound like? Okay, so have you heard about sculpting? A sculpture is making the things from a rock, okay, using the devices that he can so meticulously change the property of that bulk material in forming the selective material that we want. Okay, so one example I have given is this Mount Rushmore, but we can have various things that we see. Do you know these food grains? Okay, wheat, jawar, bajra. What is the property? They are the ones that we consume, but do we consume them like that? We make them into fine powder, right? So that flour then we are able to knead into a dough. Okay, so is it possible for us to prepare the bread from food grains? No, unless and until we convert them into the tiniest possible particles, we are not able to knead them in a dough, which is a basic requirement for the formation of a bread, isn't it? So this is a top-down approach that we are using on a daily basis. So now is it correlating? Isn't it? So if you start looking at the surroundings and make observations, you will find many things that are present around you. So these nanometer materials can be present in various dimensions, from 0th dimension to the 3-dimensional structures. So 0th dimension means an atom. Then we go to 1-dimensional. So it has only one parameter of an object, which is in a nanometer size. So here we consider what are the 3 dimensions. When we are talking about the material, we have the length, breadth, and height. So height. So 1-dimensional materials have only one dimension in nanometer range. So the examples are thin layers and coatings or thin films. The 2-dimensional materials has only length and breadth. They are in nanometer range. So here you look at this nanowire. This and this, these two dimensions are now maintained in nanometer scale. And the 3-dimensional materials has all the parameters, that is length, breadth, and height in the nanometer range. So this is a spherical particle which has all of them in the nanometer dimension. And based on this type of material, we have different applications. Now, why we say that small is good nowadays, right? So if you look at the particle size, this is a bulk material, okay? And then if we cleave it into the further from 10 centimeter to 1 millimeter, yes, we have reduced the size. And if we further go down from micrometer to nanometer, we here you can see that the surface area of that particular material is increased tremendously, right? So can we use of this property? And what happens when we go from the bulk material to the nano size material? If you look at some of the properties, we see that the nano objects are lightweight. Yes, obviously, because we are cleaving them in tiniest particle sizes. So obviously, they are lightweight. They can perform the function very fast as compared to their bulkier counterparts. They are more energy efficient, cheaper, as well as they show different properties at very small scale. Okay, so these are some of the advantages of these small sized materials over the bulky materials. And what changes with change in size? First is the surface area to volume ratio. Okay, so look at this cube, which is 5 millimeter by 5 millimeter in dimension. So if you want to calculate the surface area of the cube, the formula is 6 into side square. Side is 5 millimeters. So the area of the first cube is about 150 millimeter square. If you go to the next one, what you see is the same size, that means volume of the cube is same, but we are now cut it into 8 different or eight small cubes. So here the surface area of the cube is increased. Similarly, if you go from here to here and then to the final structure that we are looking at, the surface area has increased manifold from 150 in the beginning to 1200 here. So likewise, we go on cutting the same material into the tiniest possible particle size to get the maximum surface area. But what you see here, the surface area is changing, but volume is remaining same. So that means if in a given unit volume, the surface area of the material is increasing, the reactivity also would be increasing. Okay, and that depends on the some of the properties are dependent on the surface to volume ratio. And if you calculate the surface to volume ratio by using the formula that is given over here, you see that from 1.2 for the first cube, we have it going to 9.6. So obviously, relatively, with the same volume, we are getting the increased surface area as well as the surface to volume ratio is also increased. Okay. And because of that, the rate of reaction increases if we are going to use such tiny particles to carry out some reactions, catalytic reactions. Okay, so coming to the properties of nanomaterials then. Some of that already I have talked about. So largely, we can say now is that the properties at nanoscale of any material are different for two main reasons. A large surface area, which leads to high chemical reactivity. And this large surface area eventually leads to the changes in their electronic properties. Then, as the size goes down, the quantum effect starts to come into picture and they dominate the behavior of the materials that are formed. And therefore, we see the size-dependent properties such as quantum confinement in semiconductor materials and superparamagnetism in the magnetic materials. Sometimes the non-magnetic materials become paramagnetic. So for example, gold, it is non-magnetic when it is present in a bulk. Okay, but if you go down to nanometer size, it starts showing some magnetic properties. So what is the origin of these properties? We have to go deeper, slightly deeper into that to get a clear picture. So if you look at the bulk material, when we are going to talk about the semiconducting properties of these materials, we say that there is separation, presence of a valence band and a conduction band. So valence band means the electrons are, this valence band is occupied, okay, fully occupied. So there you have the maximum occupancy of the electrons, and the conduction band is unoccupied. So depending upon the transfer of electrons from the valence band to conduction band, the properties of the bulk material would change. And that is how we have the conductivities of the metals, okay? And we can control the conductivities of superconductors by doping different materials or elements into the basic material. Okay. And here, if you look at nanoscale material, there is separation between the valence band and conduction band. So because of this, what happens in bulk material, we have closed line bands. And because of less uh, gap between the valence and conduction band, the unbound electrons have motion that is not confined. They can freely move from the valence band to conduction band. Whereas when you reduce the particle size, because of the separation between the valence band and conduction band, the electronic motions are now restricted. They are most of the times confined in the valence bond. And that is where the quantization phenomena that comes into picture. Okay, so that is the origin of the properties that you are going to see when you are reducing the size of the material. Now, what are the different properties? The first thing that comes into picture is if I am preparing nanomaterials from the metals, okay, metals are usually conducting electricity, they are conducting temperatures, okay. So is that property going to change when I am going to reduce the particle size? So here, first we will look at the temperature, melting temperature. So most of the atoms which are present on the surface, most of the atoms are present on the surface of the nanomaterials. And therefore, these nanomaterials have more unsaturated bonds as compared to their bulkier counterparts. And because of this, the surface energy that is associated with nanoparticles or nanomaterials in general is quite higher than the bulk materials. And because of this, the temperature, melting temperature of the nanomaterials goes down compared to bulk materials. And this relationship between the melting points of a bulk material and a particle or a nanomaterial is given by this equation, which depends on like this radius. It defines the size of the material, okay, which affects the latent heat of fusion also and surface energy as well as density. So here again, I would like to pose a question to you, dear students. What would be the density of a bulk material and a nanomaterial, which will have higher density? And you will have to, whatever may be your answer, you will have to support your answer with the reasoning. Okay, unless and until we try to do that, it will not be possible on our part to understand clearly how exactly it happens. Okay, so always, whenever you do not understand anything, start asking questions to yourself. And if you are finding answers, write it down. If you are not finding answers, always go to the textbook or any other open educational resources that are available in plenty on the net right now. Visit the official websites, okay? And there you will find always the authentic material. and try to understand. That is my request to you. Okay, so this is about the melting temperature. Then how it is going to affect the electronic property. Now electronic properties means what? Okay, electronic property means if there is change in the electronic levels because of the reduced size of the material, then obviously the transitions, electronic transitions would be affected tremendously. And when we are talking about electronic transitions, in front of my eyes, I see various, what you say, band of colors that are appearing. Okay, because the electronic transitions, you know, if you have studied in BSc, DD transitions, FF transitions, there are metal to ligand charge transfer transitions. Then N to pi star or pi to pi star transitions are the same. What are the differences? And the differences, are they making changes in their properties? Yes. So when you have transitions from the one of the d orbitals to an empty d orbitals, there is change in the color that is reflected in the color of the salt or the complex that we are synthesizing. That is not the only thing. There are other things that are associated with it, but this is one of the things, isn't it? So that is a bulk material. Can it be possible when we have the smallest possible sizes of the materials? Yes, obviously, because here we are seeing that when we have a bulk material, this we have already seen, because of the less gap between the valence band and conduction band, the properties are different. And here, as in the nanomaterials, if you are changing the sizes from 50 nanometers, for example, to 1 nanometer, there is change in the speciation, electronic transitions, therefore would be greatly affected, and then the properties would be changing. Obviously, the electrical properties also would be changing because the conductivity of electrons would define the electrical conductance of a material. So in general, the electrical conductivity of nanotubes or nanorods, which are different materials, would be very high. Why? Because of the confinement of electrons to the particular direction, because of confinement into a particular band, that is valence band. Okay. And we can correlate this, like you have a river which is flowing freely. The dimensions are not specified. Okay, so the water that flows through the river has a different rate as compared to the pipe that we are using to supply the water to our home, right? The dimensions are changing, right from the river to the diameter of what you say, pipe which we have at home, and the pipe the municipal corporation lays, right? So we can restrict the rate of flow of water in such cases. Similarly, if we have the confined environment, or in the electronic states, the different states, the electrons are confined, yes, obviously their electrical properties would also be changed. What about the optical properties? Yes, this I have talked about here to some extent when we were looking at electronic properties, right? So the color of a material is determined by the wavelength of light that they absorb, and not just absorb. What we see is the light that they emit. Okay. So as we know that nanomaterials can be formed in different sizes, then each size will reflect a different color. Why? Because the electronic structures would be then varying. So here I have taken an example of gold nanoparticles where you can see that these are atomic, then 4 nanometer, 15, going to 60 and 100. So here it is yellow in color, Then as you increase the size, there is transition from the color in the color from yellow to red to pink to blue. Material is same. What is changing? Just the size. And with the change in size, what is changing? It is the electronic transitions. And that is reflected because the electronic transitions, as they are changing, the amount of light as well as the wavelength of light these are absorbing are different, and therefore the light they are reflecting and that we are seeing here is different. Okay, so can we then tune the properties of uh, nanomaterials so that we, if we want the nanoparticles of red color only? Is it possible? Yes, obviously it is possible. That is what we are seeing here. But next question comes, initially I said that it depends on shape and size. Here we are talking just about or with respect to size. What about the shape? What are the different shapes? Okay, the shapes are nanoparticles, then we have nanorods, and then we have nanospheres, nanotubes, etc., etc. So if I am taking gold only and changing the shape from the nanoparticle, which is spherical, to a nano a rod or nanofiber, to a nano disc, to a nano uh, tube. Would the properties be changing? And looking at this, I would say yes, the properties would change. And now here, um, uh, what is changing, we can see. So this structural characterization of the nanoparticles by a variety of spectroscopic techniques like atomic force microscopy, scanning electron microscopy, or transmission electron microscopy, etc., can give us the idea about the size as well as shape and structure of the nanoparticles that we are synthesizing. So here again, I have taken an example from this paper of a gold nano shell, which has a spherical structure, and a gold nano cage here you see has a very nice cuboidal structure. And if you look at the properties with respect to the dilution, you see that there is change in the optical absorbance, which is reflected in the transition of the lambda max. Okay. Similarly, for the gold nano cages, we see the differences. Now, oh, this is good, but why? Can we use this property? For what applications? Because as the material is getting tinier and tinier, the solubilities are also increasing, right? Why? Because surface to volume ratio is decreasing. So one example I can give you here is if you are consuming a tablet like a paracetamol, which is a 250 milligram tablet, you are taking it orally. So uh, if you have to give paracetamol to a small child or a person who has a phobia in swallowing the tablet, what do you do usually? You crush it into a powder and give it to that particular person. Okay, so if we are uh, keeping the volume constant, that means the 250 milligram is the constant volume in both the cases. In one case, you are giving the tablet as such. In another case, you are crushing it and giving it. So which one of these two will have the higher rate of dissolution, and that would be reflected in alleviating the pain that a person is suffering from, okay, or reducing the temperature because it is an analgesic, isn't it? So here again, if you look at the surroundings and what exactly is happening, if you start correlating, you would see that It is an amazing world of materials which remains to be exploited still for different applications coming in the future, because the electronic devices, they are getting tinier and tinier, right, due to advancement in this nanotechnology. And also I would like to know, a person, do you know that someone has got a Nobel Prize in chemistry for constructing nano machines? Okay, and I would be showing, so they have shared the Nobel Prize, okay, and one of them was from a country, and a person from that country already had utilized this property nano of the nanomaterial, which was a great invention at that time. I will show you his picture and the invention in a few minutes. Okay, so bulk, if you look at the bulk gold we use for making the ornaments, right? This is non-catalytic, it is very inert, right, at room temperature. And unless and until we convert them into the salts, they would not react to form different complexes, right? So here it is very shiny, inert material. But as you go down to nano size, you look here, the colors are changing, the properties are changing, with respect to the structures also. And as the size is decreased, you have more surface areas, that is the area that is available and exposed to the surroundings, so that the faster rate of catalytic conversions can be achieved. Okay, so that I'm skipping. Now we go to the mechanical properties. Now what are the mechanical properties? We need to have strength to a material. For example, the simplest material I can give example of is the cement. Okay, the curing of cement. Or then we have the materials that we prepare for, lightweight materials. We prepare for aeroplanes, right? So can we use nanomaterials uh, in preparing those materials used in aeroplanes, so that they become lightweight and will have more strength than the existing materials? Yes, obviously that would be exciting. And recently, I don't know how attentive you are, or how you uh, give attention to the media, excluding the unnecessary things. A gas cylinder, the LPG cylinders are coming in a very lightweight materials. Okay, so usually female at home are dealing with these cooking gas cylinders, and the existing ones are quite heavy. And if you want to change the cylinder when it goes or the gas is over, then that person has to lift it if it is at some other place. So if we can prepare or think of making such material which can withstand the high pressure, because LPG, it is an LPG, that is liquid petroleum gas. That means the natural gas is liquefied under pressure. So the material in which you are confining this liquid petroleum gas has to withstand that pressure also. So it is not a very simple thing. So can you prepare materials having such high mechanical strength and toughness, so that even if you drop it, it will not break? Okay. Even if it has high pressure inside, it will not break. So that is where the application of nanomaterials in giving the mechanical strength or toughness to a material comes into picture. Uh, so uh, that also depends on the properties like Young's modulus and tensile strength that can be measured using some equipments. Okay, it's carrying out some physical measurements in the lab. So here I have given a comparative account of 3 different materials having different sizes, and how the Young's modulus is changing, and you can correlate the strength of these materials in general with these properties. Now, why we need to investigate the mechanical properties. So far we have seen that the materials, when they reach nanoscale, their properties change. And we have to take advantage of their properties, their potential to investigate further properties or usefulness. And since these properties are dependent on size, we do not have a better understanding. So far, if you look into the literature, thousands and thousands of papers have been reported. Many materials are there, but what about the applications? They have not studied. They have just synthesized by using different synthetic procedures that I have not looked or covered here because of the time constraints. But there are different, two only the most commonly used synthetic procedures I have talked about, the top down and bottom up approaches, right? But yes, their properties are still unknown. We need to explore them. And these materials, as now we have seen, have tremendous potential in developing the novel, adaptable, and incredibly sensitive devices for applications in various fields, such as like surface engineering or detection of force and light, nanofabrication. We are using these terms very frequently and routinely, but do we really understand the meaning of that? Nano manufacturing, nano machines, nano tools, what is that? Okay, and other fields like biomedical applications. And as you go down, electronic properties changes. They are not only reflected in their absorbances or optical properties, but due to quantization, their reflectance also, as well as their um, fluorescence properties also change. So you, from non-fluorescent materials, you can get fluorescent materials just by changing the size, and those can be utilized for imaging applications, either in the development of sensors or in biomedical applications. Then we can also explore the magnetic properties of the materials. Now, if I go to pain. For example, when we are preparing steel, that is also a material. The toughness as well as durability of steel depends on the like grain boundaries. If you have many defects in that, the material is not very good. So, can we eliminate those kind of defects in the material so that a uniformity can be achieved, so that the durability and the mechanical strength is achievable. So the steel in general, you see, has low or negligible magnetic moment. And the material that usually is being used in the steel is a carbide of iron, Fe3. See, that is the carbide of iron. So if you look at this body-centered cubic structure of this iron carbide, okay, you have these atoms placed at the corner and the center. Each of them now will be showing the orientation of the electron spin in one particular direction. Okay, so this may lead to increased, so this is the magnetization of material. So you can change the property. This is just a simple basic example I have given. Here you have the electron spin, and there would be an orbital momentum also, but usually that is nullified, the effect that is coming into picture due to orbital momentum. But the spin magnetic moment would be contributing towards the magnetic properties of the materials. And this orientation of the magnetic of the electron spins, when you are going down from the bulk to the tiniest sizes, is greatly affected. So that is where we say that super magnetic materials come into picture, or super ferromagnetic materials that come to picture. Where are the applications? You have seen that the trains which run with the speed of about like 400 meters per hour, okay, that are based on they use magnetic levitation, and the materials that they are using are your lanthanides. They are very, very costly. So is it possible for us to prepare or use such kind of nanomaterials and can be used for which are cheaper, present in bulk, so that the cost would be reduced tremendously and can be applied for day-to-day application to make the human life very smooth. We have to think about that in that direction. Okay, so so that is one of the things. What I was going to come in is this is the application of the magnetic nanoparticles. This scientist, Lou Ottain, he is from the Netherlands, or was, because unfortunately we have lost him in the last week. He died at the age of 94 on 10th March 2021. He was the one who invented the first cassette tape which utilized the magnetic nanoparticles. And he was also the first one to take it further to the compact disc, the CDs that we are using right now. So transition from the magnetic cassette tapes to the CD also was under his investigation or his invigilation, right? So unless and until you understand the properties, you will not be able to apply it, okay, and tune it for our as per our needs. And there are only 2 to 3 slides now I would be talking about. So when we are looking at this, one has to ask, is this technology really very recent, or was it known earlier? People have started looking at the history and they found that thousands of years ago, Chinese were using gold nanoparticles to introduce the tinge of red colors into the pottery they were making. Then French windows, okay, yes, they were coated with the different colored nanoparticles to reflect different colors, the French windows, right? Then in ancient Indian history, if you look at, particularly in Ayurveda, you find different bhasmas, bhasma, the gold bhasma, suvarna bhasma, or the tamra bhasma, whatever it is, they were using bhasmas to treat the arthritis or other underlying ailments. What was the sizes? The sizes were varied based on the treatment that was given to the material in preparing those formulations, right? And according to the treatment, their properties were also changing. Okay, so this nanotechnology, we can say now, is not new. It was known to our, or it was known to ancient civilization, like about thousands of years ago. And in 1857, Michael Faraday, you see him here in the picture, he prepared gold colloidal particles and prepared the solutions you see here. And they were stable for a century. And during World War II, people destroyed them. Okay. But if they were now, I don't have any doubt that they would have been stable to date also. Okay. So looking at the properties and the stabilities of these nanoparticles and variety of applications that can be achievable, yes, this is an area to investigate further. Now, here I have given few applications in the biological system or biomedical applications. Can we use them for drug delivery applications? And I have not gone much into the details because of the time constraints, but let me tell you that if we are going to use different capping agents, we can decorate the nanoparticles with different functionalities, including we can attach specific um, antibodies or specific peptides so that targeted approach can be utilized to deliver the drugs which are loaded with medicinal with the nanoparticles having anti-cancer activities. Okay, why directed approach can be possible? Because we can modify the surfaces. That is an advantage. And they come here, you see, in various shapes and sizes. Okay, and this is another field that is coming into picture, and that would bring in different or variety of drugs for the treatment of many diseases where where the usual drug particles cannot go, these tiny particles can get access to. Okay, so yes, many of the drugs, even if they are highly effective because of their sizes, they cannot cross the cell membrane. So in such cases, if you can prepare the nano carrier kind of things, having the nanoparticles loaded with the drug, you can achieve that purpose and can utilize those effective drugs for the treatment. And here, as I mentioned, the optical as well as fluorescent properties of the materials also would be affected by reduction in the sizes. You can inject them into the experimental animals disease and send them to the tumors to identify the location of the tumor so that the targeted therapeutic approach can be used without harming the normal cells and thereby reducing the toxic side effects that a person who is undergoing chemotherapy, that can be reduced tremendously. Okay, so my dear students, you can see that by changing the particle size and shape, how many properties can be changed and put into different applications. The sky is the limit. So now the world is yours. And with this, I thank you all for your kind attention. And if there are any questions, I would be happy to answer them. I hope, like, I don't know how much time I had taken, but okay.
Thank you, madam. Thank you, madam, for nice lecture. We almost covered all the basic properties of the nanomaterial. This is really wonderful lecture and beneficial for the students.
Yeah, thank you.
Now, the lecture is open for discussion. Students, any questions? You just raise your hands. We'll unmute you. Already finished.
I'm sorry if I exceeded the time. I think it is 55 minutes. Okay.
No, it is within the time, madam.
Yeah.
Students, any question? Please ask.
Hello, ma'am.
Yes.
तर मॅम मला असा प्रश्न होता, जर आपण वेगवेगळ्या सिंथेसाइज मेथडने एकच नॅनो पार्टिकल जर तयार केलं तर त्याच्या प्रॉपर्टीज मध्ये काही चेंज होतील की नाही?
होतील. येस, होणार. ऑब्विसली हे पहा, केमिकल वेपर डिपॉझिशन इज वन ऑफ द टेक्निक्स. मी आत्ता फक्त काही नावं घेते. So if you synthesize the nanoparticles by using either top-down approach, then bottom-up approach, there also you can see the variation depending upon how you are treating the material, what kind of starting materials you are using. There you will be finding various changes. Though they are smaller changes, they would be reflected in their properties. So same material can be synthesized by using different techniques, but they will have different sizes, different thickness, and that would be again reflected in their properties. Yes, yes.
Okay, thank you, ma'am.
Yes.
Any more question from the participant? All participants can unmute themselves so that they can ask the question. Okay, there is no more question. Just students, you have any question, you just put in the chat box. We will forward you to the madam also.
Okay, no problem. My pleasure. I would be happy to answer them. Yes.
तुम्ही क्वेश्चन विचारला होता डेन्सिटी मध्ये काही चेंज होईल का बल्क आणि नॅनोच्या
Uh-huh. Yes, I'm happy that you remembered
तर
that. Huh?
डेन्सिटी मीन्स मास अपॉन व्हॉल्यूम असतं. मास आणि व्हॉल्यूम दोन्ही स्केलर क्वांटिटी आहेत ना.
Huh?
तर मग तर डेन्सिटी मध्ये चेंजेस नाही होणार.
Correct. I'm very happy. I'm very happy. So you are now thinking, right? Mass is not changing. The volume is not changing. So the density is mass upon volume. Very correct. Okay, I'm very happy. Yes, density will not change. Yes.
Okay, thank you all the participants and thank you madam for a nice and wonderful lecture. One small announcement to the all participants. Please write your name and college name in the chat box.
Okay. Thank you, Arbut sir.
Just 1 minute, madam. There's one small query from Dr. Manish.
Good morning, madam. It was a very nice talk.
Thank you.
So when we talk of size contradiction in metals especially, will metal nanoparticles show intermittent conductivity or will they show semiconductor-like behavior?
Again, that depends on, like, if we are using a pure metal, okay, so it can show the changes in the semiconducting properties. But if there are now, see, the concept of this single particle alloy has come into picture. I have read the papers on that. What they are doing when we talk about an alloy, it is the mixture of two or more than two elements. So when we are talking about the semiconducting properties of metallic nanoparticles, it is now possible to mix variety of metals to get the semiconducting materials having a better properties. It is possible. Yeah.
Okay, madam.
They are called as single particle alloys, but they are not single particles because you have at least two metallic particles coming together. So it is not single particle, but the papers that they are using the term is single metal alloy, but single particle alloy. It is not single particle.
They are basically a cluster of particles.
Cluster of particles. And if you change the ratios of that, also will be reflected in different properties, similar to other nano doped semiconductors.
Okay, madam. Thank you, madam, for a wonderful talk.
Thank you. Yeah. Thank you once again for giving me this opportunity.
Tomorrow we will meet again. All the participants will join tomorrow at 10:30 a.m. so that we will start the lecture around 11 a.m. Thank you all, and today's meeting is over. Thank you.
Yes, I will leave the meeting now. Bye.
Yes, madam.